In this lecture, I'm going to discuss what it means to learn in a reinforcement learning problem. In reinforcement learning, there are two main types of tasks. Previously, we discussed what I called the prediction problem. That is, given a policy pi, find the associated value function v of s. The second type of task is called the control problem. This means to find the optimal policy pi, which leads to the maximum v of s. In other words, the control problem is maximizing the sum of future rewards. You've already known since the beginning of this section that this is our goal. Now we can accurately define what this means and thus find a solution. First, we need a little bit more math and a few more symbols to accurately describe what we are doing. You already know about the value function given a state v of s. To be more precise, we refer to this as the state value function. There is another quantity known as the action value function, where the value depends both on the state s and the action a. We denote it with the symbol q. As you can see, it has almost the same definition of v of s, except that it's also conditioned on the action a. And so in the Bellman equation, since a is given, we do not sum over the policy distribution. One interesting question to consider from a computer science perspective is how much space is required to store the value functions. Let's consider the scenario where both states and actions are discrete and that we have a finite number of them. So let's say we have big S states and big A actions. In this case, we can store the state value function in an array of size big S. But for the action value function, we'll have to store it in a two-dimensional array of size big S times big A. And thus, the storage required for Q is quadratic, whereas the storage required for V is only linear. Okay, so why do we need this concept of the action value? Well, this is going to help us find the optimal policy. Remember, some policies may be good and some policies may be bad. The optimal policy is the best policy, the one that maximizes the value. First, let's just think about how to compare two different policies. We can say that policy 1 is better than policy 2 if v of s given pi 1 is greater than v of s given pi 2 for all the states s in the state space. So this helps us describe the relative goodness of different policies. From here, we can define the best policy and the best value function. The best value function is the value function for which there is no greater value function. It's the max over all possible policies of v of s given pi. So we'll denote it with the symbol v star. Similarly, the best policy will be the argmax over all policies pi. So we call that pi star. So far, we haven't needed to invoke the action value function, but let's see how it's related. First, the optimal action value is defined similarly to the optimal state value. It's the max over all possible policies pi of q given pi. We'll call this q star. This must hold over all states and all actions. Furthermore, the optimal state value is equal to the max over all actions from the optimal action value. So from this we can define the relationship between q and v. The real value, no pun intended, of the action value function is this. Suppose we are playing some game and we would like to know what's the best action to perform right now. Well, we have a dictionary telling us exactly what to do. All we have to do is find the argmax over q given a state s. In other words, the best action to perform becomes a simple dictionary lookup. As a side note, notice how the optimal policy is not unique. It could be that multiple different policies lead to the same best value function. In this case, it suffices to find just one of them. On the other hand, the optimal value function is unique, because if there are two different value functions, then logically one of them must be greater than the other one. Before moving on, let's think about what a good first approach might be to actually finding an optimal policy. Remember, this is called the control problem. Suppose we are playing a game like Grid World or Tic-Tac-Toe, where our state space and action space are both finite. In this case, a naive search can solve this problem. First, let's create a list of all possible policies that can exist. Obviously, some may be bad and some may be good, but one or more of them can be defined to be the best. Then, in a loop, we can test each policy. So first we call a function to find the value for the current policy. So that's the evaluate function. Remember that, as we discussed earlier, this is just a linear algebra problem. Then, once we have the value function, we can compare it to our current best value function. If the new value function is better, then we make this the new best value function and make this policy the new best policy. When we are done looping through all the policies, we have found the optimal policy. In the next lecture, we'll discuss these two functions here in greater detail. You may have noticed that we don't yet really know how to implement them. What I would like you to know now is this. First, the evaluate function, finding v of s given a policy, is not all that hard. In fact, we already discussed how we would do this if you knew both the policy distribution and the environment dynamics. It becomes a simple system of linear equations. In the next lecture, we'll look at a more practical way of implementing this. Second, the other function, enumerate all possible policies, is conceptually simple but impractical. As an exercise, you may want to try implementing this in code for a simple example like Grid World. In other words, while this method here appears to be nice and simple, it is not actually practical to do.